Morning, everyone. We are starting today on the second of our talks about operational amplifiers. And I wanted to spend a little bit of time talking about some of the common ways that op-amps can be set up. And these are sort of, I think of them almost like recipes. You know, hey, you need to do this. There's a particular way you can set up an op-amp circuit to do that, right? And there's actually a bunch of those types of things that if you just do some internet searches, you're bound to find ways to do certain types of signal processing tasks by just finding some sort of an op-amp recipe, so to speak. So I'm going to go through a few of these today, and the goal that I have is not for you to memorize all the little formulas that we get for this kind of setup or for that kind of setup. It's more along the lines of practicing our rules that we have for being able to look at any old op-amp circuit and being able to tell someone what it does just based on the two fundamental rules that we're working on for these ideal op-amp circuits. Okay, so that's kind of, I wanted to say that first thing is that the goal is not for you to memorize everything that we come up with today. The goal is for you to see how we came up with it, right? So that's kind of the big idea. The two rules, just to make sure we remember these. One is there can be no current flowing into or out of our input pins of an op-amp. Okay, so if we're talking about flowing of current, and kind of label that on here, something like this, there can be no current flowing into or out of either of those input terminals. Okay, and that's one of the desirable things about an op-amp is that it doesn't, if that's true, that there's no current that flows into or out of the input terminals, then that means it will take no energy to actually do or to kind of excite the op-amp in the way that it needs to be excited. The second rule is that there will be no voltage across the inputs. So if you think about, kind of think about putting a voltage maybe here relative to here, that's going to be 0 volts across those two input terminals. Okay? This one is a little bit different than the first one in that what causes that rule to take place is that there has to be some form of feedback mechanism that is actually actively trying to put those two pins at the same voltage. That's functionally how an op-amp circuit really works. The good news is I'm only going to give you op-amp circuits where it is already set up that way, that it will tend to try to make those two inputs tend toward 0 volts. It's probably good for me to mention it is possible to set up op-amp circuits that don't do that, and in those cases then you can't use these rules in order to analyze them. But almost all of the op-amp circuits that are out there are set up so that the feedback mechanism that's built into the op-amp circuit will tend to put those two terminals at the same voltage as one another. Okay? What I'd like to do is go through several of these commonly used op-amp circuits, and I thought I might do it a little bit in the form of a game. It's like, name that op-amp circuit. Okay? So to kind of warm up with this, I put a very, very common one, but it's pretty easy, up here first. There's one right over here. So what you see is that there could be some kind of circuitry that's out there in the world, and it's creating some kind of a voltage signal that it is feeding into the op-amp circuit, which is over this little chunk over here on the right, is the op-amp circuit. Okay? Let's look at that op-amp circuit and try to determine what it does, okay? Using our rules. So no current on the inputs and no voltage across the inputs. So what does that mean as far as the voltage at the inverting terminal of this circuit that I've got up here? I've got a label over here that is the output voltage, V out, and I've got a wire that has nothing else in the wire, and it's literally hooked right back up into the inverting input. So what voltage do I have at that inverting input relative to this ground terminal down here? It's not hard. That will be V out, right? Because you're hooking it straight up into that terminal. So you're on your inverting terminal, since it's got a wire hooked right up to it, it's going to have a voltage of V out. What does that mean the voltage has to be on the non-inverting terminal? V out. okay, assuming that this has a proper feedback loop on it, and it does, okay, it is going to have V out on that non-inverting terminal. Well, what would you call that in terms of this circuitry that's pumping something into this circuit? Okay, I would call it something like maybe V in, right? That V in is this voltage that you're feeding into this thing in the first place. So what does this circuit do? Don't overthink it. This circuit does this. V out is equal to V in. Isn't that fun? All right. For that reason, this thing is called a voltage follower. Now, many of you are probably sitting there going, why do you need that? Okay, that's kind of my next little thing. Why would you ever want a voltage follower? All right. Well, let me give you two ideas as to why a voltage follower might be a useful thing for you to have. Remember that on the inputs of your op-amp, there is infinite impedance, or there's at least very high impedance if you have a real op-amp, right? That means that whatever circuitry you have that's generating this signal, it will not seem like, it will not seem to that circuit as though it's connected to anything, because it's not going to have any ability for current to flow. So it doesn't demand any power out of the circuitry that's generating the signal, right? And that can be a very desirable thing, because if you demand some kind of power out of that circuitry, it very well could have the effect of changing what that signal looked like, right? As soon as you make that signal drive some kind of real thing, it could actually change what the signal's nature is, or what it looks like, right? So having a high input impedance is often a desirable thing when you are amplifying a signal. And then two, the output is capable of sourcing current, and so therefore, because it's capable of sourcing current, it's also capable of sourcing power. So if you want to basically have something that follows the voltage of a signal, but is able to actually pump power to the thing that needs the power, right, by being able to put current out of the output, right, a voltage follower is something that you could do that. It follows the exact voltage, but it's able to deliver power where you don't want perhaps the source signal to have to deliver power. Does that make sense? Okay. So that's kind of our warm-up. Voltage follower. We just named that circuit. Are you guys ready to play the rest of the game? There might be some prizes, right? Learning is occasionally its own reward. I know, everyone hates that, right? Okay, let's play Name That Op-Amp Circuit. Okay, are we excited? So round one, and keep in mind, there's only two rules for this game. No current on the input terminals, right? And no voltage across the input terminals. Here's round one. I've got some circuitry that's creating a voltage signal that's putting an input voltage into the op-amp circuit. Okay, so I want to know, what is this op-amp circuit over here doing? How do we go about trying to determine that? Okay, tell you what, for a lot of these, one of the very first steps you might want to think about is defining what a ground voltage might be. So I'm going to do that over here and say that's my ground voltage down there. That way I can label voltages on my figure relative to that ground voltage, and I don't have to always do the plus and minus logo kind of thing, right? So if this is my ground terminal, how much voltage do I have on my non-inverting input? Not a trick question. I have a wire hooked straight up from my ground to the non-inverting input, right? So how much voltage do I have there? 0 volts. And if I have 0 volts hooked up into my non-inverting input, then how much voltage do I have on my inverting input? Okay, that's also 0 volts. And that means everywhere along that node is at 0 volts relative to ground. Okay? So if that's at 0 volts relative to ground, and I also know that V out is at some voltage that may not be 0 relative to ground, could I determine how much current is flowing on R2? Okay, let me define it. Let's say I've got a current that's flowing right here. I call that I. Okay, what is I going to be? Okay, V out. If you want to, you could go minus 0 volts, right? Because you have 0 volts at that node in the middle over what? R2. Okay, so far so good. Now here's another question. How much current flows through this little branch in that circuit? Right, this one right here that kind of, imagine, you know, you've got a wire hooked up there, so you might be suspicious that some current might flow there. But how much actually flows coming down off of that branch? 0, right? There's nowhere for it to go because we're saying 0 current on the input terminals. That's one of our rules, right? So that means how much current flows through R1? The same as what flowed through R2, right? That's also just I, right? So that means I should be able to write another expression here, and I'm going to do it this way. 0 volts minus V in over R1. Okay? Now, can I rearrange that maybe a little bit and isolate V out? Because that's probably what we're interested in, is what kind of voltage comes out of this op-amp circuit. So can I do that? V out, I can multiply both sides by R2. That's going to be R2 over R1. Okay. The 0 volts is just 0, right? So I could ignore that. What I'll do is I'll pull that negative sign of V in out in front, and all this ends up being is R2 over R1 times V in. So that is how it behaves. Okay, now let me give you an idea here, or a definition of something. This stuff right over here is often known as gain. Okay, the stuff I put in the parentheses right there. That's a certain amount of gain. What that essentially is a multiplier, because you presume that your R1 and your R2 are probably not varying, right? If those are just fixed resistors, those are just values, and so your ratio of R2 over R1 is just going to be a value, and that's a lot of times known as gain, okay? And so we have a negative gain on this, which means if you put a positive voltage in on V in, you're going to get a negative voltage out for V out. And not only that, but you can scale what that output is relative to the input based on the ratio between R2 and R1. So knowing all that, who has an idea of what we could call this op-amp circuit? Okay, a voltage gain. That's not a bad idea. What do you think maybe we should acknowledge that little negative sign right there? Okay, tell you what we'll call it. We'll call it an inverting amplifier. Okay, the inverting part is the fact that if you plug a positive voltage in, you're going to get a negative voltage out, and vice versa, right? And you can just have a linear amount of gain based on a ratio between R2 and R1. Okay, now I'm going to give you one other little thought right here before I leave this idea, and that is, it really doesn't matter what the absolute values are of R2 and R1. What matters is the ratio between them, right? So a lot of times what is done in these kinds of circuits is those values tend to be brought fairly high. Why do you think that is? You know, on the order of maybe, you know, kilo ohms at least, or maybe tens or even hundreds of kilo ohms. Why do you think that they might want to bring those values high like that? Any ideas? Okay, I started off by showing you the voltage follower and said, hey, there's 0 amount of current that's going to flow from your input, from your source signal for your voltage follower. Now for this one, do you have 0 current flowing for your input signal or not? Where does I go? That goes into your input, right? Or coming from your input, or whichever way that it's actually oriented, right? But there's going to be some non-zero current now that's flowing from your circuitry. And that may not be desirable, because now that means you have to have some kind of power that is driving. If you have voltage and current that are both non-zero, you have to have some kind of power oriented or associated with the circuitry that's generating the voltage signal. How do you minimize that effect? Ideas? How about increasing R1 and R2? What does that do to I? That decreases I, and that gets you closer back to the state that we were talking about a while back, where you have zero current flowing from the terminal of your signal source. Does that make sense? So that's a lot of times something that is done, is they want to get those values high enough so that there's a negligible amount of current that's actually making the circuit work. All right, questions? Who's ready for round 2? Name that op-amp circuit. Okay. Where do you want to start with this one? I'll tell you what, I think I might do this for all of them, actually. Let's identify a ground node first. That way, when I label voltages on here, they'll be relative to that ground node. Okay? So now what? Let me seed an idea right here. What if I label a voltage right here, okay, and I'll just call it V sub I, just for give it a name. Okay, so V sub I is the voltage right in between those two resistors right there. All right? Now, can I figure out what VI is in terms of other parameters that I have for my circuit? What would be a good tool to be able to do that? Okay, let me do one thing first. How much current flows up here? Okay, I equals 0 right there. So that means I really only have a series circuit that comes from where V out is up here, down through R2, then through R1, and to ground. Do we have a nice clean formula that deals with a situation like that to find what the voltage is going to be, right, at the middle point for a pair of resistors like this, where we've got a voltage across the whole thing? Voltage division, right? So if I use voltage division here, I can say that VI is going to be equal to V out times what? VI, another name for VI, is just the voltage across R1 relative to ground, right? Okay, so what I'm going to do is pick R1 and put that in the numerator, and then I'll put R1 plus R2 in the denominator. That's my voltage division formula. And that's essentially what we need, because where else does VI exist? Right? You have 0, whenever you have a circuit like this with a properly set up feedback mechanism, you're going to have the same voltage on both of your input terminals. And if that's VI up there, what's VI actually equal to? V in, right? I said V in was that voltage that's being fed into that terminal up top. Now let me go ahead and isolate V out. V out is going to be equal to R1 plus R2 over R1 V in. Or another way that this is sometimes expressed is, you'll see there that you can divide individually the R1 divided by R1, and then you can do plus R2 divided by R1. So another way that this is sometimes expressed is 1 plus R2 over R1 V in. Right? So how does this one behave? How does this circuit behave? Whatever the signal that comes in, let me ask this question. You know how the last one, it negated that signal. That was part of what it did, was negated the signal. Does this one negate the signal? It does not. It basically has this gain value that is, you're taking the signal and multiplying by a gain value of 1 plus R2 over R1. But it leaves the two signals to where they have essentially the same sign as each other. Okay? So what do you think you might call this circuit? And don't try to get too creative. The last one was an inverting amplifier. What do you think this one might be a good, name to call this one? How about a non-inverting amplifier? Okay? Now at this point, I usually have someone who has a question and they might want to know, do you have one that's a non-inverting amplifier that has the same form as the last one? The last one seems simpler, right? All you had was just a ratio of two resistances, and that gave you a gain. This one, you have 1 plus a ratio of two resistances, a little bit more to that, right? Not only is there a little bit more to that, you'll notice what's the minimum amount of gain you can get out of this circuit? 1 to 1, right? 1 to 1 gain is the minimum. How would you get that? Yeah, R1, you essentially have to have a 0 R2 or an infinite R1, right? So anyway, the point is you can't have a fractional amount of gain, right, coming out of this type of a circuit. So, the big question is there a form of this that gets you the same thing as the inverting style, right, where it's just a ratio of two things but it doesn't invert? Well, one way to do that is you can chain two op-amps together. Do two inverting op-amps. The first one inverts it, and then the second one inverts it again, and you can get a result that way. But there isn't a circuit that is kind of straight up the exact same as the inverting style that we did with round 1, but is non-inverting. Okay? All right. Shall we go to round 3? This one's a little different. So the first two that we looked at right there were operating on only one signal each. Like one signal came in, one signal came out. Okay? This one here, we're putting two signals in, and we're getting one signal out. So we have to express what is that output signal in terms of the input signal and in terms of the other values that I have for my op-amp circuit. Okay? Where would be a good place to start with this one? Easy answer to that, because I already told you, right? What's a good place to start? Identify a ground node. Okay? And I'm doing that so that my inputs are both defined relative to that ground node as well as my output defined relative to that ground node. Okay? Now, where can we kind of start with our approach to this? Notice all 4 of these resistors have the same value in this one. And that makes this just a little bit easier. For instance, can you tell me, if I call that value right there like I did on the last one, call that VI, can you tell me what that VI is going to be? Well, let's do it. It works kind of the same as the last one where you could use voltage division, right? So VI is going to be equal to V out. What does voltage division say VI is going to be? V out times R over R plus R. Or what is that? V out over 2. And some of you probably saw that right from the beginning, but that's where it comes from, is the fact you can do voltage division right there. Okay, so that's V out over 2. Where else do I have VI? Again, assuming that you've got a functional feedback mechanism that keeps this thing stable, what do you know about the voltage across the two inputs? That means your VI value is going to be the same on your two inputs. So that means I can say VI is also going to be the voltage right there at that point. Okay? Now let me do this. Let me define a current. What if I say I've got a current of I flowing right here through my R? It's going to come down, and then it looks like there's a possibility perhaps that it could branch where that I comes down into the non-inverting terminal of the op-amp right there. but does the current actually branch? Okay? It can't, because no current is allowed to go into the op-amp on that non-inverting terminal. So is there another place where I could show I? If I defined that rightward I on that R that's up top, I would say that means I better have I that flows this way too. It's going to be the same I that flows all the way around that circuit right there. Okay, those are a couple of I's that I've got. Let me ask this. Can I do something similar to round 2 and go ahead and figure out what those I's are going to be in terms of voltage differences, kind of like we do in nodal analysis? Okay, see some heads nodding. What that would look like is V1 minus VI over R. This is going to be equal to I. But what else is I equal to? Would you say that I should also be equal to VI minus V2 over R? Now, because those two R's have the same value, what's an easy simplification I can do at this point? I suppose it wouldn't be equal to I anymore, but if I erase the I over there, I can cancel out those two R's, and V1 minus VI is going to be equal to VI minus V2, right? Now, is there substitution I can do? Right? V out over 2, I should be able to sub that in right there and right there. So that means that V1 minus V out over 2 is going to be equal to V out over 2 minus V2. Now let me do this. I'm going to add V out over 2 to both sides of the equation, and I'm going to add V2 to both sides of the equation. Okay? That means I will have V1 plus V2 over here. This is going to be equal to V out over 2 plus V out over 2. But that's an awkward way to write V out. Right? So I'm going to rewrite it as V out is equal to V1 plus V2. So what does this circuit do? Okay? It combines the voltages. It literally sums the voltages, right, for two different signals. So what do you think we might call this circuit? Again, the trick to this is don't be too creative. This is called a summing amplifier. Although I could be sympathetic towards someone who wanted to debate whether or not it's an amplifier. Why is that? It's not necessarily amplifying much of anything, although it could be, right? It has the ability of delivering as much current as it needs to, right? Up to whatever the limit is of your op-amp. But it has the ability of delivering some heavy current if need be, okay? And if you select high values for R, it will also have the ability to not demand a lot of current out of the source signal circuitry, right? So you could say that it's amplifying, or it has the capability of amplifying current, but it's not really amplifying voltage. It's just adding two of them together. Okay? Now, you might wonder why I put these little pictures over here. Voltage signal 1 that has like a little profile to it, and then a voltage signal 2. What this does is it takes those two signals and it literally adds them together the whole way along there. So if I have -1 at the beginning and +1/2, it's going to add to -1/2, right? If you then have +2 and add that to a -1, where's it going to go then? +1. So that's where it'll be for that little chunk. And then it goes to -1 for voltage signal 1 and +2 for voltage signal 2. What's it do from that point on? It actually holds at the same value, right? Because whether I have 2 minus 1 or whether I have -1 plus 2, I end up at 1 either way. So I'm just wanted to give you a visual of what this is doing. It's taking these two voltage versus time signals, adding those two signals together, and that becomes an output signal. Isn't that neat? All right. Any questions? Who's ready for round 4? Let's do round 4. This one gets a little trickier, but I know that you guys are up for it. So round 4. Again, we have 2 different inputs for this one. We have a voltage signal 1 and a voltage signal 2. It feeds into a circuit. This one does actually have differing values, only we only have 2 different resistor values, right? R1 and R2. But R1 exists in 2 places, and R2 exists in 2 places. Okay? And what we want to do is express what is V out in terms of my input voltage signals. Where's a good place to start? Again, identify a ground node. So I'm going to do that first. That way when I label voltages, they will be assumed to be relative to that ground node. Then what? How about I label a voltage right there on that non-inverting input of the op-amp? And like I've been calling them before, I'm going to do again. I'm going to say let's call that VI, that voltage right there. Do I know enough stuff about my circuit to where I could express VI in terms of inputs and resistor values? We have 0 current that can flow into that non-inverting input. That means that any current that's coming from voltage signal 2 is going to go through R1 and then down through R2. And that sets up a perfect application, again, of a voltage divider. Right? And VI, another way to say that is the voltage across R2. Okay? So when I say VI down here, VI should be now equal to V2 times R2 over R1 plus R2. Now, where else does VI exist? Okay, I've said this several times now, but it does depend on there being a proper feedback loop, but I will represent to you that this one does have a proper feedback loop that will cause the 2 input terminals to attain the same voltage, right? So we're going to say VI is that input voltage on the non-inverting input. It means VI is also the voltage on this node that's connected to the inverting input. So far, so good? Now, what do you think I'm going to do next? Okay, just like I did for the last one we just did, how about I define a current, right? What if I define a current that flows from right to left on R2, and I call that I? What is I going to be? Okay, should be V out minus VI over R2, right? Now, how much current flows where it looks like this circuit maybe could branch? How much current can flow out of the circuit at that point? 0. Why? Because if it tried to flow, that would mean I had current flowing into my inverting input of my op-amp, and that can't happen. That's one of our rules, right? So that means whatever I have flowing through R2, that better be the same I that I have flowing through R1. Okay, so that means I should be able to write that as VI minus V1 over R1. Now, what do you think I'm going to do with VI? I can sub in, right? I figured out what VI was here in terms of V2 and my resistance values. So I can sub that in for VI in this formula. And while I'm doing that, let me also multiply both sides by R2, because that'll put it in a form that I like a little bit better. So what I'm going to do there is I'll have V out minus VI. I'm subbing in V2 times R2 over R1 plus R2. This is going to now be equal to R2 over R1 times V2 times R2 over R1 plus R2. And then over here, I'll have minus V1. Now let me do this. Let me add this V2 times R2 over R1 plus R2. Let me add that to both sides of the expression so I get V out all by itself. Okay, so, and let me also multiply through this R2 over R1. Let me multiply that through this expression so that I'll basically have V2 times R2 over R1 times R2 over R1 plus R2 minus R2 over R1, V1. Okay, but now I'm going to add to this V2 times R2 over R1 plus R2. So what I did is I multiplied through the parentheses right there by R1 over R, or R2 over R1, and then I added to both sides V2 times R2 over R1 plus R2. Now, here's the strangest step of how to try to break this down a little bit better, okay? And you might say, well, I don't know why you're doing that, but go with me for a second. What if I take a fraction over here, this fraction of R2 over R1 plus R2, and multiply by another fraction of R1 R2 over R2 times R1. Is that allowed? Why is that allowed? That's a really fancy way of writing the number 1, right? So that's something that I am certainly allowed to do. By writing it that way, though, it becomes obvious that I can eliminate this R2. I can divide that out, okay? It also may become obvious to you that that leaves me with R2 over R1 as a fraction, and R1 can become a new numerator of this fraction, right? The R1 becomes a new numerator of that fraction, and then the whole thing gets multiplied by R2 over R1. What's the method to my madness here? Okay, you'll notice that I actually have a factor now for every single term in here of R2 over R1. See that? So I can factor that out. So that's the first thing I'll do. V out is going to be equal to R2 over R1. Okay. Then what's left? V2 times R2 over R1 plus R2. I'll tell you what, I'm going to pull the other term that has V2 next to it. I'll have V2 times R2, excuse me, R1 is what's left over in the numerator over there, over R1 plus R2. And then lastly, I'll have minus V1. Can I factor out a V2 from those first two terms? What does that leave me with if I factor out a V2? It'll be R2 over R1 plus R2 plus R1 over R1 plus R2, right? I'll tell you what, I'll go ahead and write it all out. R2 over R1 is going to be equal to V2 over, or V2 times. Do those have the same denominator? They do. R2, that means I can combine these two. R2 plus R1 over R1 plus R2 minus V1. And now that, in that expression right there, is another fancy way to write what? The number 1. So that means that this expression says that V out is going to be equal to R2 over R1 times V2 minus V1. All right? That was a lot of stuff, but what were we trying to do? What's our game that we're playing here? Name that op-amp circuit. What is this op-amp circuit named, do you think? Again, the little tip is don't be too creative. This is a differential amplifier. Okay? And what is its job? Okay? It takes two signals, and it takes the difference between those two signals, V2 minus V1. It subtracts the second one from or V1 from V2, right? It subtracts V1 from V2, and then applies a gain to it of R2 over R1. So it amplifies that difference. Okay? Now, some of you might look at that and go, I thought that's what the op-amp did to begin with. Isn't that what the op-amp does already, is take a difference in two voltages and amplify it? This sure seems like a lot of effort to build all this circuitry around it. Why not just plug in two voltages into the inputs of an op-amp? Because that's already what it does, is it amplifies the difference between two voltages. Why do we not do that? Okay, you might remember the model of an op-amp that we had basically said you take these two inputs, right, and you find the difference between them, right? That would be like a V in, okay? And what's inside of the op-amp? You'd had a gain of G multiplied by the V in, and that became the basis. I'm not going to have enough room to draw it here, but it became the basis for the voltage that came out of a dependent voltage source, right? Now, the only reason I bring all that up is you multiplied V in times G. What value are you going for G with an op-amp? What's your gain value, kind of your native gain in an op-amp? What is that gain value? What are the manufacturers trying for? I heard someone say they're going for a very, very large G. Okay? Now, you might not want an infinite G. You might want to be able to specify what kind of gain you want. Okay? So that's the big advantage of doing something like this and having an adjustable differential amplifier. Cool. All right, so that is the end of what I was planning on doing today for this talk. We might at some point look at some more op-amp circuits, but I think the main point, just to reiterate it one more time, the main point is not that you memorize what all these op-amp circuits do, right? The main point is that you know how to get into them, and by applying those two rules, right, no current on the inputs and no voltage across the inputs, you can analyze a whole bunch of different kinds of circuits, and you don't have to memorize the formulas. Okay? Fantastic.